Now let's come to the introduction of definite integrals. Before we come to the introduction of definite integrals and the difference between integration and definite integration, let's come with the basic introduction of calculus. Now we know that calculus is generally originated because of two major issues, geometrical issues. Has originated because of two geometrical issues. So basically the integrals or the differentiation or integration has originated from two major complex issues which the mathematicians were striving to resolve. One was finding the equation of tangent of a curve, that is, if I have the curve, finding the equation of tangent for the curve, and the other is finding the area between the curves. So this is how the calculus has originated, where the curve is given by y equals f of x, and here they are given by y equals f of x and b. So differentiation helps in finding the equation of tangent because the slope of the tangent is assumed as f dash x. This is how differentiation helps in finding the equation of tangent, and hence the mathematicians could resolve finding the equation of tangent easily, finding the derivative of the function f of x, and hence differentiation has its significance in finding the equation of tangent to any curve y equals f of x. Similarly, the next geometrical concept which was unresolved by the mathematicians was finding the area of the curves. If I have the curves like perfect curves like triangle or a rectangle or any other normal curve, we can easily find area of triangle or area of rectangle or area of parallelogram, etc. But what if the curve is irregularly shaped? How do I find area of this curve? How do I find area of this curve is the biggest question when we challenge in the field of mathematics. Finding the area of this irregular shape is not possible through any standard formula, but we use integration to solve these kind of problems where we find areas of irregular shapes. And let's see how definite integration has originated from this unresolved issue of finding the areas under the curves or areas of irregular shapes, etc. Definite integrals connected with geometry. Now, as we have seen in the introduction of definite integrals, that calculus has two unresolved issues, one being finding equation of tangent line and the next being finding the area under the curve. So let's connect with the curve. X-axis, y-axis, origin. Now I have two lines, x equals a and x equals b, which are parallel to y-axis, and I want to find the area under the curve which is this. How do I find area under the curve which is irregularly shaped? This can be done using integration, and this kind of integration is called definite integration. The area under this curve is found using as given by this shaded region is given by integral. Now because this area is bounded between x equal to a and x equal to b, we always say that these two are the boundaries, where this is the lower boundary and this is the upper boundaries. So this is bounded between x equal to a and x equal to b. So we have integral x equals a to b of f of x dx. So area under the curve is given by this, and which is called definite integral. Because this integration gives a definite value. Therefore, definite integral does not have constant of integration c, because it is definite without any unknown constant c. Is how the definite integral is originated from finding the area under the curve. So definite integral is integral a to b f of x dx, where a is called lower limit and b is called upper limit. Now let's see the notation for definite integral, which is denoted by integral a to b f of x dx is and formula which is given by f of minus f of a. That is, by substituting x equal to a in the integral first, and this is how we obtain the formula. Here a is called lower limit and b is called upper limit, and fx is integration of f of x over dx, is how we understand each of them. So definite integral of a to b f of x dx is f of b minus f of a, which is definite because it doesn't have an integration constant. So it's very important to note that definite integral does not have c, the constant of integration, and hence is definite. Is how we understand the definite integral as compared with integral. Integral has integration constant. Definite integral does not have integration constant. Partition. What is partition in integration concept? Now, when it comes to, say, I have two real numbers a and b such that a is less than b, then if I just represent them on the number line, I see that here is a and here is b. Then the partition denoted by p is said to be x1, x2, xi minus 1, xi, xi plus 1. This is said to be partition of the closed interval AB denoted by this number line, including A and B with filled in circle, is said to be the partition of AB if I have the condition that my A, which is assumed as x naught, the first term, and my B, which is assumed as the last term is such that a equals x naught is less than x1 is less than x2 is less than x3 xi minus 1 xi plus 1 equals b. That is, if I take on the number line my x naught, then comes x1, then comes x2, x3, xi minus 1, xi plus 1, and so on and so forth, xn minus 1 to n minus 1 and xn is how, taken in that order, we call this P as partition of AB. Is how we define. Therefore, partition of the closed interval AB is x0, x1, x2, so on and so forth till xn, where a and b are real numbers on the whole of the number line. Now next, let's define the norm of the partition. That is, let P equals x0, x1, x2, x minus 1 xn be the partition of AB, where a and b are real numbers. So if this is the partition, then norm of the partition P is denoted by norm P, and it is defined as maximum of each of this minus this, and this minus this, and this minus this, this minus this, and this minus this. That is, when I take this x1 minus x0, x2 minus x1, x3 minus x2, and xn minus 1. So each of this with max of is called norm of the partition P, denoted with norm P, and it is maximum of each of the lengths, the norm of the partition P. If I have the closed interval AB denoted on the number line as A and B, with this being denoted by x0, and this is x1, x2, so on and so forth till xn minus 1 and xn, then the subinterval of this taken as, say, xi minus 1 xi is called the subinterval. This is called subinterval of the whole interval AB, and length of this subinterval is denoted by delta xi, which is given by the formula length of subinterval xi minus 1 xi is denoted by delta xi, and this is xi minus 1 is how the length of subinterval denoted by this equals this. Now for the interval AB, we have various types of partitions which are denoted with P. So the set of all partitions is denoted by set of all partitions of AB is denoted by P of AB. and it is defined as P such that P is a partition of AB. So this is how we define the partition set, or set of all partitions. Set of all partitions of the closed interval AB denoted by P of AB as P such that P is a partition of AB. Set of all partitions and its notation. Let's define Riemann sum for the topic of definite integral. So what is a Riemann sum? Now the definite integral is said to be originated from Riemann sum, dedicated to the famous mathematician Riemann. So coming to Riemann sum, initially I assume a function f from the closed interval AB to set of all real numbers. Now f from closed interval AB to set of real numbers be a bounded function. Now what do we mean by bounded function is the biggest question in this sentence. When I say bounded function, that means the function has limited real number on the left and on the right. Mathematically, we define, that is, there exists m belonging to R such that mod f of x is less than or equal to m, is how we mathematically define the boundedness of a function using the real number m. So therefore, I assume that f from AB to R is a bounded function, and for this I also assume that P is equal to the first value being x0 assumed for A, and next being x1, x2, x3, xi minus 1, xi, and xi plus 1, and xn minus 1 and xn is what we call as partition. We have already defined for this B the partition of the closed interval AB. And let me take some interval Ti is closed interval xi minus 1 and xi. So I assume the interval Ti as xi minus 1 and xi, for which I am going to define the Riemann sum. So with the assumptions of f being a bounded function and P the partition of AB and the interval this, we know that the length of the interval delta Ti is nothing but xi minus xi minus 1, or this is how we define the delta Ti. Now, assuming on this, we define the Riemann sum denoted by SPF. The Riemann sum denoted by SPF is defined as summation I running from 1 to n of f of Ti delta Ti, f of Ti delta Ti is what we get when we assume this. So the Riemann sum is generally denoted by SPF and is defined as sigma running from I equal to 1 to n f of Ti delta Ti, where f of Ti is the function as defined with the closed interval AB to the set of real numbers, and delta Ti is the length of the interval xi minus 1 or xi, or you can also define this with delta xi, but both are the same, denoted by this. Now let's define the definite integral using the Riemann sum. So now we know that the Riemann sum denoted by this for the partition P and the bounded function f is defined as sigma I running from 1 to n f of Ti and delta Ti. So using this definition of the Riemann sum, the lower integral, the definite integral is defined as integral a to b using the bounds for the function, because the function f is bounded, and f of x dx, where a is called the lower limit and b is called the upper limit. So using the boundedness of the function, we have the lower limit which is a and the upper limit which is b, and hence the definite integral using the Riemann sum SPF equals summation I equals 1 to n f of ti delta I is defined as integral a to b f of x dx. Also, as I see this integral, we see that the bounded function f of x as seen in this integral is called the integrand. The bounded function f of x is referred as integrand of the definite integral this. Therefore, the Riemann integral of the function f of x is defined using this as limit norm p tending to 0 of SPF with the partition norm tending to 0 of this, and therefore we substitute this and into the function. That is, this reduces to limit norm p tending to 0 of SPF, which is summation I running from 1 to n of f of ti of delta xi, which is xi minus 1, which we have because the interval ti is xi minus 1 and xi. So using this interval, I have my Riemann sum defined as integral a to b f of x dx, which is limit norm p tending to 0 summation I running from 1 to n f of ti xi minus 1, which is called the Riemann integral of f. Of the function is how we define the integral connected with Riemann sum SPF. Now next, let's see the condition for existence of a definite integral. Now that we have defined the definite integral, now the question comes on what conditions does the definite integral exist. Now, condition for existence of definite integral says that integral a to b f of x dx exists if the condition is if f from closed interval ab to set of all real numbers is continuous. The continuous function, which has already been discussed in the previous sessions. The condition is this exists if this is continuous. So if the function is not continuous, then we say the definite integral a to b f of x dx does not exist. In this case, this being continuous, only then this exists. Is how we understand the condition of existence of definite integral a to b f of x dx. So let's finding integral a to b f of x dx using limit of a sum or the Riemann sum. Is what we're going to discuss for the session. So in order to find integral a to b f of x dx for the limit of a sum, we have the formula integral a to b integral 0 to p of f of x dx. The definite integral 0 to p f of x dx is defined using the limit of a sum as limit n tending to infinity of 1 by n sigma I running from 1 to Pn of f of I by n is how we get this formula, and we just use this in finding the definite integral as the limit of a sum. So let's see some example problems through which we understand this formula more better. Now let's take an example problem where I need to find integral of 0 to 2 x squared plus 1 dx as the limit of a sum. Now this plays a vital role in understanding the method, because the question clearly says find integral of this function x squared plus 1 with limits from 0 to 2 over dx as the limit of a sum. Now since the question is exclusively on finding the integral through limit of a sum, we use the formula which we use for finding the limit of a sum. So here, as I see this integral, definite integral 0 to 2 x squared plus 1 dx, and when I compare this with the formula which I have taken in the previous case as integral 0 to p of f of x dx, then I clearly see that my p is 2 and my function f of x is x squared plus 1. So based on these two concepts, let's find definite integral using the formula for integral 0 to p f of x dx is limit n tending to infinity 1 by n sigma I running from 1 to Pn of f of I by n. So let's use this formula in order to find integral of 0 to 2 of this. Therefore, integral 0 to 2 of x squared plus 1 dx would be expanded as limit of n tending to infinity and 1 by n summation I running from 1 to Pn, p being 2, this extends from 1 to 2n, and f of I by n, which is x squared plus 1, which reduces to I by n whole square plus 1, using x squared plus 1 expanded through the function f of I by n. So this reduces as this, and this on further simplification limit n tending to infinity 1 by n sigma I running from 1 to 2n of I square plus n square by n square is what we get as the limit. Now the question comes on how we expand this summation and then use the respective formulae. Now continued from here, my integral 0 to 2 of x squared plus 1 dx reduces to the limit of the sum as limit n tending to infinity of 1 by n sigma I running from 1 to 2n of I by n whole square plus 1 is what we get here. So let's expand this directly with summations running from I1 to 2n with each value of I substituted in the function of the summation. So in this case, I get limit n tending to infinity of 1 by n, and the summation which runs with I equal to 1 initially has first I equal to 1, which gives 1 by n whole square, and the next value of I, which is 2, gives us 2 by n whole square, 3 by n whole square, and proceeding similarly, the last value is 2n, which I get as 2n by n whole square of this. And next I have sigma I running from 1 to 2n of 1 is nothing but 2n, because it is independent of I, so I get this to be 2n. Now each of this value substituted gives me this, which on the next step is limit n tending to infinity of 1 by n, and then taking n common, because in each of the cases n is common, so I get this as n square coming out, and I have the numerators which are left inside the brackets as 1 square plus 2 square plus 3 square till 2n whole square plus 2n is how we get the summation. So each of n square in the denominator is taken as LCM out, and we get this. Now this further reduces to limit n tending to infinity of 1 by n cube of 1 square, 2 square, 3 square, 2n square of plus 2n is what we get in the next step. Now as we know that this is clearly in the form of the sum of all squares which are integers, we have as an exclusive formula for this, which we're going to substitute in this case. So let's recap with the formula which we have identified here for 1 square plus 2 square plus 3 square till 2n square. Now continued from here, we know that the sum of squares of integers, consecutive integers, 3 square till n square is n times n plus 1 into 2n plus 1 by 6 is what we have as the formula which we're going to substitute here. So therefore I have this reducing to limit of n tending to infinity of 1 by n cube and 1 square, 2 square till 2n whole square is n into n plus 1 into 2n plus 1 by 6 is what we get when n is replaced with 2n on the right hand side, plus 2n is what we get. Now this, on further simplification, gives limit n tending to infinity of 2 1s, 2 3s, 1/3 of n 2n plus 1, 4n plus 1 plus 2n of 1 by n cube. Now this n cube is taken inside, but before this we have limit n tending to infinity of 1 by n cube 1/3. When n is taken common out of this can be written as